So in this video, I'll introduce Air Constellations, which was done as a collaborative project at Microsoft Research. So Air Constellations is a new technical approach, platform, and techniques we build to enable flexible cross-device interactions. It supports a unique semi-fixed style of multi-device interactions, and it does that by using multiple self-spatially aware amateurs to which users can then easily attach tablets and other devices. They can then move, reorient, and pose these devices, forming dynamic in-air formations that suit their current task, social situation, and ergonomic needs. And this affords an interaction metaphor where relative orientation, proximity, and continuous movement into and out of these formations can drive context-sensitive interactions. Now in the next few minutes, I will give you an overview of the project, introduce our technology, guide you through a number of application scenarios, and end with a brief discussion. Our research is motivated by the need for more flexible personal workspaces at home or in the office where people can use their devices working in concert. The general motivation of cross-device computing is to leverage the complementary roles afforded by individual devices to support a wide range of application scenarios. And while many cross-device setups are either fixed or mobile, we are in particular interested in the third emerging category of semi-fixed configurations. The goal here is to preserve the modularity and rapid reconfigurability of mobile setups, while at the same time allowing physical rearrangement of diverse configurations as the task and situation demand, facilitating people's rich practices of spatially organizing information. We designed Air Constellation as a platform to support this semi-fixed style of cross-device computing. Air Constellation's workspaces are composed of 2 to 5 flexible amateurs with attached devices, such as tablet computers, allowing easily physical movement and positioning of devices around a workspace. Users can move, reorient, and pose devices together to form multi-device assemblages, with devices not only flat on a table, but floating in front at varying angles arranged into new workspaces. We retrofit multiple off-the-shelf mounts with low-cost sensors to determine the spatial location and orientation of the amateur. Here we use 4 IMUs and 2 rotation sensors for each arm, and then combine the tracking information for each arm into a unified model of device assemblages around the workspace. To inform the design of this new category of mid-air spatially aware cross-device setups, we synthesized a design space along 16 key dimensions. These dimensions include characteristics of the spatial configuration, such as physical arrangement, orientation, structure, or layering, and interaction behaviors with dimensions such as motion, direction, or spatial sensing. To illustrate techniques all across this design space, we implemented application mockups with a prototyping tool that uses the sense information of 3D position and orientation of formations to drive implementations of application behaviors, responding to any changes of orientation or proximity between devices. The goal of this prototyping tool was to allow quick and lightweight experimentation with dynamic application behaviors, and we were in particular interested exploring how Air Constellation applications could dynamically respond to users' interactions with the formations when they move devices in and out of formations, change the orientation of devices, and so on. We'll now go through a number of use case applications, and these examples will illustrate how we use flexible physical arrangement, feed-forward of transition options, and layering of devices in air across a variety of multi-device app scenarios. First, our multi-device video conference application allows dynamic reconfiguration of the task and person space. Views of remote participants can be moved to separate devices as physical proxies, resulting in a meeting experience with spatial gaze awareness and easy access to the shared whiteboard. The application also facilitates lightweight transitions from group chats to face-to-face side conversations when breaking one of the remote proxies from the formation. And participants can use spatial-aware gestures for sharing documents with individuals, or instead tilt their device for sharing with a group. And we added feed-forward techniques to many of our application scenarios for revealing interaction possibilities when moving devices closer together. In productivity applications, users can distribute tool palettes between devices for easier access, and application windows can move between devices either as automatic default behavior in response to proximity or after manually confirming any of the options revealed through feed-forward. Now, using physical keyboards attached to Air Constellations allows proximity-dependent input redirection, and moving a tablet next to the keyboard then can trigger context-dependent soft keyboard extensions. In another example, for data analysis, users can quickly assemble multi-device display arrangements without the need to manually change system settings, and they can easily change the configurations when needed. They can also form larger interactive horizontal surfaces by moving devices together. And here, feed-forward animations indicate possible formations of devices, and once joined, all devices can be used like a single continuous surface. Breaking up device formations by moving a single device allows the direct transition from shared to personal interaction, for example for overview and detail techniques. Many other applications are possible. For example, air constellations can provide orientation-aware windows and semantic zoom of controls in a flight simulator game, and in a companion setup together with a digital whiteboard, we can use device proximity to open ad hoc portals for direct transfer of sketches. We also explored system-wide cross-device behaviors. For example, when devices physically overlap, see-through portals across desktops can facilitate joint access and transfer of files or applications. And layering of devices can facilitate cross-device window management and lightweight application migration through selecting from a semi-transparent preview. Let me close with a brief reflection on the potential of dynamic in-air device formations, as well as limitations and possible next steps. First, spatial-aware tracking in air constellations allows using proximity and location as an implicit parameter for fluid interaction techniques. Now, we leverage this in several of our techniques, such as feed-forward, but at the same time, such automated tracking and the technical overhead that it brings with it might not always be needed or desired. Second, it is also important that we design for easier transitions between fixed, semi-fixed, and mobile configurations. With the ever-changing workspaces, home office locations, and dynamically evolving device ecologies, it becomes critical to best support such ad hoc working patterns. Third, we have to consider the trade-offs of proactive application behaviors. Now, as we showed, sensing the proximity, relative orientation, or adjacency of displays affords certain automatically sensed transitions in application states or behaviors. However, people's natural socio-spatial literacy implies that such device motions and configurations are also already part of the vocabulary of human-human interaction, so we have to find techniques addressing this potential design tension. Fourth, we can explore other use cases and form factors of devices and amateurs. For example, dynamic in-air formations could be applied in AR or VR applications, in education, or in specialized domain expert workspaces. So in summary, we introduced air constellations which afford highly flexible and dynamic device formations. Users can bring multiple devices together in air with 2 to 5 amateurs posable within a workspace to suit the demands of their current task, social situation, app scenario, or mobility needs. Air constellation devices, in combination with appropriate applications, feedback, and interaction techniques, open up an intriguing new design space. And the scenarios we demonstrated represent only a subset of this design space of highly dynamic and easily reconfigurable personal workspaces with in-air device formations, and we hope our work will inspire many promising research avenues to explore.